In 2023, the James Webb Space Telescope made a remarkable discovery around GJ 486b, a rocky planet just 26 light-years from Earth. This world, despite orbiting its star in less than 2 days, showed something unexpected: an infrared signature of water vapor. When astronomers first studied the faint red dwarf star GJ 486, it seemed like just another unremarkable point of light in the Milky Way. These small, cool stars burn at low temperatures and live incredibly long lives. From Earth, this particular star is invisible without a telescope, hidden in the constellation Virgo. If you're drawn to the unknown, subscribe and join the journey as we continue exploring the mysteries of the universe. In 2021, subtle changes in starlight revealed a companion, a planet roughly 1.5 times Earth's size. Its orbit is incredibly tight, completing a circuit every 1.47 days, so close that it would easily fit inside Mercury's path in our solar system. The planet receives almost 70 times more energy than Earth gets from the Sun, with surface temperatures reaching a scorching 430 degrees C. Researchers initially assumed they were looking at a dead, airless rock. Red dwarf stars are known for violent flares and magnetic storms that blast surrounding planets with charged particles, stripping away atmospheric gases over time. By all logic, no atmosphere should remain. This super-Earth, with a density of about 7 g per cubic centimeter, is likely composed of iron and silicate rock similar to Earth, but with a slightly higher metal content. Its characteristics make it a perfect laboratory for studying planetary evolution around dim stars. The planet is almost certainly tidally locked, with one side facing perpetual daylight and the other endless darkness. If someone could stand on its surface, they would experience gravity 3 times stronger than on Earth. Movement would feel slow and heavy, like walking underwater. The critical question remains: is the detected water vapor coming from the planet itself or from the star it orbits? The discovery challenges previous assumptions about planetary atmospheres in extreme environments. A rocky world burned under its parent star's intense glare, with rocks glowing a dull red. Its night side remained perpetually dark, potentially plunging hundreds of degrees colder. A narrow twilight zone separated these extreme environments, where scorching heat and deep cold violently intersected. Without an atmosphere, the contrast would be absolute: molten stone on one side, frozen silence on the other. Despite these harsh conditions, the planet became an unexpected target for the James Webb Space Telescope. During each transit across its star, the system's brightness would dip measurably. These brief moments allowed a fraction of starlight to filter through surrounding gases or empty space, enabling astronomers to detect molecular fingerprints by splitting the light into a spectrum. Previous telescopes like Hubble and Spitzer lacked sensitivity for such small, rocky worlds. They had only succeeded with large gas giants, featuring thick atmospheres that produced clear signals. Webb's advanced 6 1 or 2 meter mirror and infrared spectrographs finally provided the precision to probe smaller planets. Ironically, researchers selected this planet precisely because it shouldn't have an atmosphere. Their plan involved using it as a control case, a simple hot rock whose featureless spectrum would confirm Webb's measurement capabilities. But nature rarely follows human expectations. Before observations began, Earth-based teams studied the red dwarf star itself. An M3.5 type star, about a third the Sun's radius, it glowed orange-red at roughly 3,300 Kelvin. Its slow rotation suggested moderate magnetic activity. Yet red dwarfs remain notoriously unpredictable, erupting in ultraviolet radiation bursts with surfaces covered in cool, dark spots. Understanding the star's behavior was critical. Light variations could potentially mimic or conceal the chemical traces scientists sought to discover. Webb's near-infrared spectrograph carefully collected data during planetary transits, with each exposure meticulously calibrated to remove noise and cosmic interference. When analysts finally reduced the data, the main transit curve initially appeared exactly as expected, a crisp dip showing the planet's passage across the stellar disk. Then, they noticed something unexpected. The detection of water appeared first puzzling. A persistent absorption feature near 1.4 microns challenged existing scientific understanding about atmospheric loss around close-in rocky planets. Initial measurements showed an effect so small it was barely above detection thresholds, just a few dozen parts per million. When scientists processed a second transit months later and found the exact same feature in the identical location, random noise became an extremely unlikely explanation. Multiple research teams independently reanalyzed the data using different correction algorithms for stellar and instrumental effects. They all reached the same conclusion: something was absorbing light precisely where water absorbs. Three potential explanations emerged. One hypothesis suggested a thin atmosphere continually replenished by volcanic activity. Deep internal heat and tidal forces might melt rock, releasing steam through fissures and vents. This outgassing could sustain a faint vapor envelope for millions of years, similar to processes on Io, Jupiter's volcanic moon, though on a much smaller scale. Another theory involved surface minerals trapping water in crystal structures. When heated, these minerals could release water vapor through thermal desorption, creating a fragile veil renewed during day-night cycles. A third possibility centered on the star itself, where water vapor naturally forms in cooler photosphere regions. However, each scenario faced significant challenges. The star's intense radiation would quickly break water molecules apart and sweep fragments into space. Maintaining a detectable signal would require perfect second-by-second balance across the entire planetary surface. The stellar water mimic was particularly compelling. During a planet's transit across a dark star spot, Webb might register stellar water as planetary water. The resemblance is so close that even high-precision instruments struggle to differentiate. Ultimately, resolving this mystery will require observations at additional wavelengths. Fortunately, a capability Webb possesses. An instrument Nyson covers a different infrared range, offering a unique perspective on water signatures. Scientists compare how these signatures change across wavelengths to determine the water's true origin. A signal growing stronger towards shorter wavelengths suggests a stellar source, while weakening indicates a planetary connection. This discovery marks a turning point in understanding planetary atmospheres. Before this observation, detecting molecular features on Earth-sized planets seemed impossible. Webb technologies now reveal incredible sensitivities, teaching researchers about both specific worlds and their investigative methods. Red dwarf systems, comprising roughly 70% of our galaxy's stars, have long been dismissed as poor habitat candidates. Traditional views cited problematic characteristics like intense flares and tidal locking. However, new models propose intriguing possibilities. Strong magnetic fields or constant volcanic activity might enable super-Earths to retain thin atmospheres, potentially filling the galaxy with rocky planets holding gas and water traces. This single world bridges a critical gap in planetary evolution understanding. It connects giant planets with thick, easily studied atmospheres and small terrestrial worlds where atmospheric signs are nearly invisible. Regardless of water vapor presence, the data refines techniques for analyzing cooler, more temperate targets. Science advances by confronting unexpected findings. The surprising water detection around an unlikely planet challenges existing theories about atmospheric behavior under extreme radiation. Researchers now question whether volcanic replenishment might be more efficient than previous models suggested, or if red dwarf flares erode gases differently based on magnetic orientation. Each observation generates new questions. When the campaign concluded, researchers archived terabytes of data, preparing for deeper analyses. Ground-based telescopes continued monitoring parent star variability to clarify planetary signals. Understanding the small red sun becomes crucial for deciphering the planet's characteristics. For now, the complete truth remains unresolved. Somewhere in a distant system, a small rocky world continues its silent journey, holding secrets waiting to be uncovered. and scanning the cosmos, scientists caught a glimpse of something extraordinary. Water's faint signature emerged from a distant world, captured by Webb's sophisticated instruments. The discovery challenged existing boundaries of detection. The signal appeared subtle, just a few dozen parts per million, around 1.4 microns. Despite rigorous calibration, the feature remained consistent across multiple analyses. Thousands of exposures during 2 planetary transits revealed a delicate molecular fingerprint. When starlight passed through the planet's surrounding space, certain wavelengths dimmed slightly. Each absorption pattern corresponded to specific molecular interactions. Researchers faced a complex challenge, distinguishing genuine signals from the inherent variability of a red dwarf star. Different research teams processed the data using varied approaches. Thermal corrections, background subtraction, and detector response maps differed, yet all produced the same spectral signature. This consistency suggested the signal was real. The water's potential location remained uncertain. It could be suspended in the planet's atmosphere or mixed within the star's cooler photospheric layers. Timing analysis provided initial insights. Genuine atmospheric absorption would appear only during transit and vanish immediately afterward, while stellar effects would linger or drift with stellar rotation. Astronomers explored alternative explanations, modeling the star as a complex patchwork of magnetic spots. In these regions, temperatures can drop below 3,000 Kelvin, cool enough for water molecules to form. A planet crossing such an area would block less total light at specific wavelengths, potentially creating an apparent absorption feature. The discovery transcends a single observation. It represents a moment where technology expands our understanding, revealing that the universe continually holds surprises in unexpected places. And on water's survival near extreme heat hinges on complex planetary processes. Teams delved into the feasibility of water existing in such harsh conditions, exploring multiple mechanisms that might sustain vapor. Tidal forces keep the planet's interior molten, with volcanic vents potentially releasing continuous steam. Numerical models suggest a potential balance between outgassing and loss could maintain trace vapor for thousands of years. Surface processes might also play a role, particularly through hydrated minerals that release water when heated above 400 degrees C. The planet's locked rotation creates a fascinating dynamic. On the sun-facing hemisphere, minerals would continuously generate localized molecular clouds. Conversely, the night side would reabsorb moisture into the rock lattice, creating a perpetual cycle of release and capture. However, escape velocity adds complexity. At temperatures around 700 Kelvin, hydrogen atoms move quickly enough to break free from gravitational constraints. Ultraviolet radiation from the star splits water molecules, with stellar wind carrying hydrogen away and leaving oxygen to oxidize the surface. Without continuous vapor emergence, the water signature would rapidly fade. A strong magnetic field might slow erosion, but tidal locking likely suppresses internal rotation, the mechanism that generates magnetism. Consequently, charged particles could stream directly into atmospheric layers, heating and dispersing them. The Webb telescope's precision reached a point where 2 physically different realities produced identical curves. Wavelength behavior became the next diagnostic. Planetary water absorption weakens towards shorter wavelengths, while stellar water strengthens. Webb's nearest instrument covers the range from 0.8 to 2.8 microns. Further observations with NIS could reveal the feature's slope and origin. The persistence of water would require an improbable combination of intense volcanism and residual magnetic shielding. Water signatures detected around a red dwarf have sparked intense scientific investigation. Detection methods push detector technology to its limits, with researchers carefully parsing every possible explanation. Instrument specialists meticulously cross-check their findings. Background fluctuations, pointing jitter, and cosmic ray hits were systematically ruled out. The photon signature itself remained consistent through every test. Statisticians quantified the probabilities. Planetary and stellar origins each carried roughly equal chances, approximately 45% and 55% respectively. The margins shifted with different assumptions about spot coverage and atmospheric composition. The ambiguity prompted new investigative strategies. Scientists planned comprehensive monitoring using both space-based and ground-based telescopes. By tracking stellar brightness variations and spectral features simultaneously, they hoped to clarify the water signal's true origin. Engineers prepared technical adjustments to improve measurement precision. Even tiny thermal oscillations in observatory mirrors could significantly alter absorption depth measurements. Future observations targeting cooler, smaller worlds would require extreme calibration sensitivity. Researchers developed sophisticated three-dimensional surface mapping models to simulate evolving stellar magnetic regions. They aimed to compare spectra during different stellar activity periods, looking for consistent patterns. The core question remained: did the water signature emerge from the planet's atmosphere or the star's environment? Comparisons between high and low activity periods would provide critical insights. A consistent signal would suggest planetary origins, while variable measurements would point toward stellar sources. Similar observations of cool stellar atmospheres had already confirmed water's natural presence in stellar environments. Yet, planetary contributions couldn't be definitively excluded, making this investigation particularly intriguing. Haut-Chanchan spectra from these maps will be compared directly with Webb's next dataset to determine whether the 1.4 micron feature stems from spatial temperature variations or genuine molecular absorption. Every refinement adds complexity to tracking instrument temperature, detector gain, pointing stability, stellar rotation phase, and flare probability. The ultimate goal is straightforward: confirming the presence of water beyond our solar system. Before new observations begin, NISS detectors must be recalibrated to ensure cross-instrument accuracy within 1 part in 10,000. Webb will then observe consecutive transits, capturing spectra from 0.8 to 5 microns in a single sequence. These measurements should reveal the full shape of the absorption band and its wavelength dependence. Only then can researchers determine whether the faint troughs in the data belong to a planet venting steam or the cool scars of a restless red dwarf. The measured signal strength suggests any vapor layer must be thin, probably no denser than the gas wisps surrounding Mercury. Such an exosphere would behave more like a constantly escaping and renewing plume, rather than traditional weather patterns. Even a pressure of a few microbars could scatter enough infrared light for Webb to detect. The critical question becomes whether subsurface geology can supply gas quickly enough to sustain this film against relentless loss. Tidal heating presents one potential energy source. The planet's slightly elliptical orbit means gravitational forces stretch and relax its body as it moves closer and farther from its star. This friction converts orbital energy into internal heat, potentially keeping the mantle partially molten for billions of years, similar to the mechanism powering Io's volcanoes, but far more dramatically on a world 3 times Earth's mass. Magma chambers could extend deep into the interior, with surfaces venting through wide cracks. If water or hydroxyl compounds are trapped in the mantle, these vents would release steam alongside carbon dioxide and sulfur dioxide. Near the substellar point, outgassed material would instantly split under ultraviolet light. Hydrogen would rise and escape, while heavier fragments might form a temporary veil. The balance between venting and escape rates would ultimately define the planet's visible signature, influenced by its surface chemistry. On net temperatures above 700 Kelvin, the planetary environment transforms dramatically. Minerals undergo significant changes. Iron oxidizes rapidly, silicates lose bound water, and sodium and potassium become volatile. These processes introduce new spectral lines that can complicate data interpretation, potentially overlapping with water features. Scientists must model not just atmospheric physics, but also high-temperature mineral reactions. The planet's complex dynamics reveal fascinating patterns across its day and night sides. On the night side, temperatures may drop below the condensation point of several gases. When residual vapor drifts across the terminator, it could freeze and re-enter the crust as hydrates or ices embedded in regolith. Over time, this exchange would gradually transfer volatiles from the hot hemisphere to the cold zone, subtly altering surface composition. Wind speed and atmospheric density, both currently unknown, entirely determine the efficiency of this transport. High-resolution general circulation models attempt to simulate these flows, assuming a tidally locked planet with minimal atmospheric pressure. Using fluid dynamics equations under constant stellar heating, researchers simulate fascinating atmospheric behaviors. Jets racing faster than sound emerge from the dayside into darkness, cooling, condensing, and falling back toward the surface before re-evaporating. Even at minimal density, such motion redistributes material and affects emission spectra. Secondary eclipse data provide intriguing insights. The planet's dayside radiates at about 700 Kelvin, consistent with an airless surface, yet slightly cooler than a perfect black body. This small percentage difference might result from partial heat transport by trace gases or dust lofted by micro-impacts. Surface characteristics add further complexity. The albedo, measuring light reflection, is estimated below 0.2, indicating absorption of most incoming radiation. A dark basaltic crust matches this value. Laboratory measurements of molten basalt at similar temperatures produce nearly identical infrared emission curves. If Webb's future phase curve observations confirm these findings, it would mark the first remote identification of lava flows on a rocky exoplanet. The planet's gravity, about 3 times Earth's, means molten rock spreads in broad plains rather than forming steep cones, creating a dramatically different geological landscape. Anion vicus flows hundreds of kilometers long might cross the substellar hemisphere before solidifying. The terrain would remain relatively smooth due to continuous resurfacing that consistently erases old craters. Over geological time, heavy elements could gradually migrate toward the planet's core, enriching the crust with lighter silicate materials. This process creates subtle differences that might influence spectral color. Radiation from the parent star is intense, but primarily infrared, with only a fraction appearing in the ultraviolet range that typically drives photochemistry. Paradoxically, this could help small amounts of water persist slightly longer. With reduced UV flux-breaking molecules apart, photosis slows, though stellar flares periodically spike emission to destructive levels. These weekly flares potentially sweep away parts of the exosphere. Monitoring such outbursts becomes essential for interpreting Webb's readings. Ground-based observatories with high-cadence photometers continuously track stellar brightness. When a flare coincides with a transit, it alters baseline illumination, creating artificial spectral shifts. Correcting these effects requires synchronized observations across multiple wavelengths. The planet's interior structure remains theoretical, but follows predictable models based on density and mass. Current models suggest an iron core comprising roughly 60% of total mass, surrounded by a silicate mantle and thin crust. Core temperatures might exceed 5,000 Kelvin, hot enough to maintain partial fluidity despite age. If convection still occurs, it could generate a weak magnetic field, though tidal locking likely limits rotation to 1 full turn per orbit. The resulting field would be asymmetric, stronger near the terminator where motion persists, and weaker under the static substellar point. This symmetry could significantly influence atmospheric escape. Charged particles follow magnetic lines, creating uneven shielding that means localized erosion. These invisible channels allow gas to escape more efficiently. Webb's long-term goals include detecting this pattern indirectly through spectral intensity variations. The planet's gravitational interaction with its star produces a measurable wobble. Radial velocity instruments on Earth can refine its mass and orbital shape. Combining these data with Webb's transit measurements provides a mean density precise to within 5% accuracy. Real-time data from the Las Cumbres Observatory Network and TESS spacecraft help map the star's activity cycle. When around small stars like red dwarfs, protoplanetary disks behave differently compared to those circling sun-like stars. These disks are compact and metal-rich, allowing planets forming close to the star to quickly accumulate dense cores before the surrounding gas dissipates. This particular world likely assembled from refractory materials such as iron, nickel, and silica within the first few million years of its system's formation. Any initial hydrogen and helium envelope would have been stripped away early, leaving the bare core we observe today. Water might have subsequently arrived through volatile-rich planetary migrations inward. If these impacts occurred after the star's most violent early period, some delivered water could have survived temporarily in mineral form. Geological processes involving partial melting and venting might explain the current trace water vapor signature. Scientists employ coupled thermal evolution and volatile loss models to test these scenarios. Each simulation tracks mantle temperature, degassing rates, and stellar flux over billions of years. The results predict when outgassing stops, when the crust solidifies, and which chemical species remain detectable. For this specific planet, models cluster around two potential outcomes. Either continuous low-level volcanism maintains a short-lived steam envelope, or complete atmospheric loss happened billions of years ago, leaving only surface sublimation. Infrared phase curve data collected during non-transit periods provide additional insights. By measuring the planet's brightness as it moves behind its star, astronomers can infer heat distribution. Efficiency. A sharp brightness drop suggests little heat redistribution, consistent with an airless rocky body. A gradual decline implies atmospheric circulation. Early measurements slightly favor the airless scenario but allow enough deviation to keep the debate active. Detecting emissions from specific molecules like carbon monoxide, carbon dioxide, or sulfur dioxide could help confirm volcanic activity. However, the challenge lies in signal strength, with expected absorption depths less than 20 parts per million near current Webb telescope limits. Confirmation will require data compilation from multiple transits, with work already underway to combine Webb's readings with other observations. ORNAIL's upcoming European exoplanet mission will conduct atmospheric studies with unprecedented depth. By observing hundreds of planets using complementary wavelength coverage, researchers hope to unravel complex planetary dynamics. Critical spectroscopic investigations will track potential vapor layer variability. Fluctuations in vapor strength could signal active geological regions with new vents opening or closing. Such changes would represent the first direct evidence of geological activity beyond our solar system. Surface temperature mapping through secondary eclipse photometry offers additional insights. Infrared emission shifts across successive orbits might indicate transient hotspots consistent with lava lakes or geological fissures. While no variability has been confirmed yet, upcoming observations at longer wavelengths will enhance sensitivity. Gravitational interactions with potential undetected companion planets could maintain orbital eccentricity and tidal heating. Radial velocity monitoring continues searching for these companions. Even a planetary body half Earth's mass in a nearby orbit could generate sufficient energy to keep the planet's interior partially molten. The emerging picture reveals a massive metal-rich world enduring constant stress, with its surface continuously reshaped by heat and radiation. Vapor traces hover above, fragile yet visible across vast distances. Whether this vapor originates from the planet or its star remains uncertain. The next investigative phase depends on NISS follow-up. Extended wavelength coverage will help determine if the absorption feature weakens or strengthens, coupled with simultaneous stellar brightness monitoring. This approach will help pinpoint the water signature's source. Instrument teams are finalizing critical preparations, calibration checks, detector gain alignment, and thermal stability verification. Until new data arrives, current evidence suggests a delicate equilibrium where volcanic release competes with stellar erosion and surface minerals continuously feed the exosphere. Every detected molecule represents a transient moment in a perpetual exchange between rock and sky on this extraordinary world. Webb's near-infrared imager and slitless spectrograph will extend the spectral range to capture every nuance of planetary transit. The mission's core aim is to trace each photon back to its source with unprecedented precision. During observations, the telescope records the system's brightness across thousands of narrow wavelength bins. This approach allows astronomers to build a two-dimensional map of the star's temperature distribution by analyzing how absorption features evolve minute by minute as the planet crosses different regions. The critical challenge lies in distinguishing between planetary and stellar sources of absorption. Scientists look for specific spectral characteristics. If the depth of a rough feature decreases toward shorter wavelengths, it suggests planetary origin. Conversely, an increasing depth points to stellar influence. This distinction hinges on an incredibly precise slope measurement, accurate to within a few parts per million. Ground-based telescopes play a crucial supporting role, monitoring the star simultaneously in visible light. Star spots appear darker in the optical range, so any infrared absorption dip coinciding with optical dimming helps identify the source. Coordinated campaigns involving observatories in Chile, Spain, and Hawaii are scheduled to capture these critical windows. Ensuring data accuracy requires meticulous calibration. Engineers at the Space Telescope Science Institute have spent months refining techniques, verifying detector temperature stability within a few thousandths of a degree. Webb's mirrors undergo periodic adjustments to compensate for thermal shifts that could subtly change focus. The new observations are designed to be more comprehensive, capturing the system for several hours before and after transit. These extended baseline intervals allow measurement of stellar variability unrelated to the planet, establishing a reference spectrum. By subtracting this baseline from in-transit data, researchers can isolate components truly linked to the planetary crossing. Parallel spectra and polarimetric studies from ground-based telescopes will merge with Webb's data, creating a comprehensive dataset where every spectral frame has a matching measure of the star's brightness and color at the same instant. Oranitan facilities like CFHT and HARP are mapping stellar magnetic topology through detailed observations. The key to understanding these stellar characteristics lies in polarization signatures, which reveal surface magnetic field orientation and strength. These signatures correlate directly with cool spot number and location. By feeding this information into radiative transfer models, scientists can generate synthetic spectra of the star at different rotation phases. Webb's results will help determine whether spot-induced absorption fully explains observed water band variations. Stellar rotation introduces an important variable. The host star completes a full turn approximately every 4 months. Since the planet transits every day and a half, successive crossings sample slightly different longitudes. Over several weeks, Webb will effectively scan the star's surface strip by strip. Researchers aim to align the 1.4 micron feature's strength with rotation phase to uncover spot modulation periodicity. A key diagnostic emerges. If the feature waxes and wanes with a specific period, it belongs to the star. Conversely, a steady feature suggests origin in the planet's immediate environment. Flare monitoring continues through test satellite and radio observatories. Ultraviolet bursts inject temporary water signatures into stellar spectra by cooling expanding plasma. A flare during transit could mislead analysis, so real-time alerts from TESS allow observers to flag and discard affected data before combining exposures. The statistical framework relies on Bayesian inference. Each hypothesis, stellar contamination or planetary atmosphere, is represented by a model containing dozens of parameters: spot coverage, temperature contrast, atmospheric scale height, molecular abundance, and noise terms. Using Markov chain sampling, computers generate millions of synthetic spectra, comparing them with observations and updating probabilities iteratively. The preferred solution minimizes residuals across all wavelengths simultaneously. Early trial fits with existing data lean slightly toward a stellar explanation, producing marginally smaller residuals. However, these differences remain within detector calibration uncertainty. Definitive classification awaits NISS results. Understanding stellar contamination carries broader significance. Red dwarfs dominate the galaxy, and their surfaces are far more complex than the Sun's. Star spots can alter apparent transit depths at the 0.1% level, precisely the amplitude of atmospheric signals astronomers seek to detect. NARTS are here on Earth's sized planets, Detecting accurate spectral details is crucial for telescopic data interpretation. The entire field relies on this system as a critical calibration standard. Laboratories are recreating similar spectra under controlled conditions, using high-temperature furnaces to simulate red dwarf photospheres and gas cells filled with water vapor to provide reference absorption lines. Astronomers refine molecular line lists for atmospheric retrieval codes by comparing laboratory data with Webb measurements. More precise laboratory data allows better differentiation between planetary air and stellar features. Infrared photometry plays a key role by observing the secondary eclipse, the moment a planet moves behind a star. Webb isolates the star's pure light by subtracting the combined light measured before the eclipse, which reveals the planet's own emission. Features present in both signals must originate from the star, while features disappearing during eclipse belong to the planet. This comparison requires extreme timing accuracy within seconds and stability across days-long orbits. Mission controllers schedule observations during periods of thermal equilibrium when sunlight on the Webb sunshield remains constant. Telescope temperature variations can mimic small spectral changes, and every pointing adjustment introduces minute heating. Calibration observations before and after the transit correct for these effects. If nearest observations confirm feature weakening at shorter wavelengths, analysts will proceed to quantify atmospheric properties. Retrieval algorithms translate absorption depth into scale height, the effective thickness of the gas layer. Assuming water dominates and temperature matches dayside brightness, the inferred pressure would be less than 110,000th of Earth's. At such density, molecular collisions would be infrequent, blurring the boundary between atmosphere and space. Detecting any signal under these conditions would demonstrate Webb sensitivity. Alternatively, if the slope strengthens, the signal must arise within the star. This outcome would provide the first direct measurement of water in a red dwarf photosphere and offer constraints on convection and magnetic mixing inside these cool stars. Current stellar atmosphere models struggle to reproduce molecular opacities at low temperatures, making Webb's observations potentially groundbreaking. On-sand data analysis could finally resolve hydrogen alpha uncertainty. Multiple transits will provide the opportunity to stack and process observations, with machine learning classifiers now trained on simulated spectra to automate subtle distinctions. Networks learn intricate correlations across wavelength bands, differentiating planetary and stellar water signatures. Comparing line widths of suspected water bands with known atomic features allows precise characterization. Planetary absorption broadened by atmospheric motion produces symmetrical lines, while stellar lines shaped by turbulence and magnetic fields skew slightly. Measuring hydrogen alpha asymmetry demands signal-to-noise ratios exceeding 1,000, challenging but achievable. Once validated, these models can process future datasets from other planetary systems in hours instead of weeks, dramatically accelerating scientific discovery. Upcoming missions will build on these methodological advances. The Aerial Observatory will observe hundreds of exoplanets using dedicated time series optimized for atmospheric retrieval. Multi-wavelength slope analysis, simultaneous optical monitoring, and stellar surface mapping will become standard protocol. The Habitable Worlds Observatory will extend research into direct imaging, revealing planetary composition through reflected light. At the analysis level, each new data set contributes to a cumulative likelihood function describing potential scenarios. As additional transits are processed, the curve representing planetary origin may gradually rise or fall until one hypothesis overwhelmingly emerges. Scientists expect decisive separation once total observing time exceeds about 50 hours, a threshold reachable within Webb's second extended mission. The implications extend far beyond this single target. The process of distinguishing star and planet in spectra defines the current instrumentation frontier. Photons encode overlapping layers of information, one from the star's convective surface, one from the planet's thin exosphere, and one from interstellar space itself. Understanding how to disentangle these layers will determine the success of future searches for life-related molecules. Preparations continue with meticulous precision. Telescope operators rehearse pointing maneuvers, engineers monitor detector temperatures, and software teams update retrieval codes with improved molecular constants. When the observation window opens, Webb will lock onto the star, capturing continuous spectra for nearly 10 hours, each photon carrying critical scientific potential. And investigations into small, rocky exoplanets are reshaping astronomical understanding. The search for water signals demands convergence across multiple instruments. NISS slope, optical light curves, and thermal phase curves must all agree before scientists can definitively state whether water originates from a planet's thin atmosphere or stellar features. The precision required to extract signals from planets barely 1.3 times Earth's radius has never been attempted before. Previous instruments were designed for gas giants 100 times larger, with deep, easily measurable atmospheres. Now, every collected photon teaches engineers how to improve detection methods for future targets. Rocky planets around red dwarfs represent the majority of potential Earth-like worlds within current technological reach. These small, cool, faint stars necessitate close planetary orbits to provide comparable warmth. This orbital geometry increases transit chances and enables frequent observations, but simultaneously exposes planets to intense radiation and magnetic activity. Data from these systems serve as critical stress tests for theories about potential life near volatile stars. If a world can retain water vapor at 800-degree temperatures, cooler planets in similar systems might preserve entire oceans. The underlying dynamics involve a constant contest between gravitational forces pulling gases downward and stellar energy pushing them away. Ultraviolet photons break apart atmospheric molecules, creating lightweight, fast hydrogen atoms that reach escape velocity and stream into space. Over billions of years, this process can completely strip a planet. The new data help identify the atmospheric survival line, a critical threshold determining how much radiation a planet can endure before losing its atmosphere, revealing whether planetary mass can counteract stellar violence. They will feed these numbers into global circulation models. These are the same physics engines used for climate prediction on Earth, but with adjusted parameters like surface gravity, albedo, and magnetic field strength. Simulating thousands of Saint-Fipé-Bénors, possible worlds becomes possible through this method. The simulations predict how temperature and pressure evolve with altitude and the rate at which gases are lost. When the model reproduces Webb's measured spectrum, it reveals the combination of conditions that could have produced it. Each simulation narrows the range of plausible realities. This discovery also changes how astronomers interpret flat spectra, those nearly featureless plots of light often emerging from transit studies. Previously, a flat line suggested a cloud-covered or airless planet. Now, it might also indicate stellar interference. Observers can no longer treat stars as static light sources. They are dynamic, molecularly complex surfaces. Accounting for this complexity will refine every future measurement. Understanding red dwarfs has become a top priority in exoplanet astronomy. These stars make up roughly 70% of all stars in the Milky Way, yet their detailed spectra remain imperfectly modeled. Their temperatures hover near the condensation point of many molecules. Features from water, carbon monoxide, and titanium oxide overlap in angled patterns. Laboratory spectra collected on Earth rarely extend to the high pressures and magnetic fields found in stellar photospheres. Webb's data provides the first real benchmark for these environments. Simultaneously, planetary geologists are revising ideas about internal heat and outgassing. A world 3 times Earth's mass retains its primordial heat longer. Higher pressure at the core keeps parts of the mantle molten for billions of years. Volcanic activity could therefore be ongoing even under the planet's solidified crust. If this is true, volcanic plumes might inject water vapor, carbon dioxide, or sulfur gases into a transient atmosphere. Observing similar signatures on other super-Earths would support this interpretation. It would mean that despite surface infernos, their interiors remain restless, capable of rebuilding atmospheres long after stellar winds destroy them. Measurements from the secondary eclipse campaign have already supplied vital boundary conditions. The planet's dayside temperature, hovering near 865 degrees P, corresponds almost exactly to a bare rock under direct stellar illumination. This finding limits any potential atmospheric complexity. A thin atmosphere might seem insignificant, but it reveals critical insights about planetary processes. For scientists studying rocky worlds, even minimal atmospheric signals can unlock profound understanding. Geophysicists have calculated that volcanic degassing could potentially create a continuously cycling atmosphere, neither stable nor completely disappearing. The implications stretch far beyond simple observation. When volcanic activity replenishes atmospheric gases at 10 to 100 times Earth's current flux, it creates a dynamic system that fascinates astrobiologists. Surface chemistry becomes transformed through these processes. Ultraviolet radiation breaks apart water molecules, generating free oxygen atoms that oxidize minerals and alter surface reflectivity. Detecting such minimal signals requires extraordinary precision. During planetary transit, brightness drops less than 1/100%, with absorption features measuring only tens of parts per million. Researchers must meticulously remove instrumental noise, spacecraft temperature variations, cosmic ray impacts, and thermal drift to reveal these subtle signatures. This work becomes especially crucial as astronomy prepares for next-generation telescopes. The extremely large telescope in Chile and NASA's Roman Space Telescope will soon expand our search for rocky worlds. Their success depends on understanding how stellar variability might contaminate spectral data. The discoveries from this 26 light-year neighbor serve as a reference manual for future exoplanet studies. They suggest that volatile compounds like water can survive deeper within rocky planets than previously thought. During planetary formation, water can become trapped in mineral structures, later released through volcanic activity. These observations demonstrate how minimal planetary signals can provide massive scientific insights. By carefully analyzing even the thinnest atmospheres, researchers can indirectly detect geological activity on worlds too hostile for direct exploration. Astronomers are reassessing how they define a planet's habitable zone, moving beyond the traditional view of a region where liquid water could exist on the surface. Habitability now hinges critically on atmospheric retention, not just temperature. If a red dwarf's radiation strips away air faster than a planet can replace it, even a perfectly temperate orbit will result in a lifeless rock. This insight pushes the inner edge of the habitable zone outward and may significantly reduce the number of truly viable planetary systems. Current observations provide the empirical foundation for this recalibration. Data archives become laboratories where research teams analyze every photon using independent methods. Parametric models remove stellar noise for one group, while another applies machine learning algorithms trained on synthetic spectra. When multiple approaches converge on identical parameters, scientific confidence grows. Disagreements trigger deeper investigations into systematic variations. This process exemplifies modern astrophysics, not through dramatic singular discoveries, but through meticulous iterative refinement by hundreds of specialists across continents. Even if the final verdict reveals water is stellar rather than planetary, the outcome offers more than it disappoints. It would confirm that red dwarfs can host cool, molecule-rich regions, serving as miniature chemistry laboratories that could influence planetary climates. Star spots covering significant surface areas alter radiation spectra reaching nearby planets, potentially transforming atmospheric photochemistry. Future habitability models around M-type stars will directly incorporate this effect. Measurement insights are already modifying instruments for future missions. Detector arrays now include redundant temperature sensors to monitor subtle drifts, with calibration lamps precisely covering wavelengths where red dwarf molecules absorb. The goal is creating less ambiguous data from the start. By learning from this challenging case, engineers reduce uncertainty for subsequent research. The collaborative project spans over 24 institutions. Data analysts in Arizona coordinate with modelers in Geneva and hardware specialists at Goddard. Each group concentrates on a different puzzle piece: stellar magnetism, molecular spectroscopy, thermal emission modeling. When exchanging intermediate results through shared servers, discrepancies often highlight the next investigative step. Progress unfolds through these cross-checks rather than grand revelations. Detecting molecular features on rocky worlds opens pathways for dedicated atmospheric telescopes. Funding agencies watch closely because these results justify missions worth billions. Confirming stellar contamination limits helps direct resources toward complementary techniques like high-resolution ground spectroscopy or direct imaging. The philosophical impact runs deeper than immediate measurements. Every time a faint absorption line is confirmed or dismissed, humanity's understanding of its cosmic neighborhood sharpens. Water detected near a planet 26 light-years away might not change daily life, but it redefines what counts as nearby and reminds us how fragile atmospheres can be. Worlds can lose their atmospheric protection entirely. Earth could too, under different circumstances. Observing this process elsewhere provides context to our planet's delicate balance between radiation, gravity, and life. Theoretical explorations push boundaries of understanding. At 800 High-degree silica begins to vaporize, releasing sodium and iron into surrounding gases. A trace of water could interact with these vapors to form exotic hydroxides. Such reactions influence atmospheric opacity and heat escape mechanisms. Including these interactions in models will produce more realistic predictions for superheated rocky worlds. Students entering astronomy will treat this case as their first example of data interpretation under uncertainty. They will learn that ambiguity is not failure, but a stage in discovery. A signal that might belong to a star or planet forces the community to improve instruments, revise models, and observe again. This cycle, observation, doubt, refinement, forms the foundation of empirical science. Geophysicists also examine the planet's tidal locking for insights into interior dynamics. The perpetual daylight divide concentrates stress along the terminator line. Numerical simulations suggest this gradient can drive mantle convection patterns, unlike any on Earth, potentially focusing volcanism, along a continuous ring. Might gas preferentially gather near the twilight zone, creating a steady plume of atmospheric vapor rather than global eruptions. Future observations of infrared phase curves could test this by searching for localized hotspots. Chemistry within the star gains new relevance. Cool regions on the stellar surface potentially containing water suggest oxygen and hydrogen reservoirs deeper in the stellar atmosphere than current models predict. This finding would reshape our understanding of stellar evolution, magnetic field generation, and even the spectra of distant galaxies dominated by similar stars. Whether the signal is planetary or stellar, it feeds back into cosmic models at every scale. Each observation adds another line to humanity's growing catalog of exoplanetary environments. Some planets are wrapped in thick hydrogen envelopes, others are bare and metallic, while some have ambiguous traces like this one. Together, these examples form a continuum showing how planets evolve under different stellar conditions. As data accumulate, scientific conversations have shifted from "is there water?" to "where can water survive?" This question now drives mission planning for the next decade. The answer depends on multiple variables: stellar type, planetary mass, magnetic field, and distance. All of these are measurable with current or near-future technology. Each mapped parameter space brings researchers closer to identifying a truly Earth-like world with stable, life-supporting air. In control rooms and laboratories, scientists are already preparing to apply these methods to cooler planets orbiting quieter stars. Their observations will reveal whether the boundary between airless and atmospheric worlds exists at a particular level of stellar activity or planetary gravity. Once this boundary is known, statistical surveys can estimate the number of habitable worlds in the galaxy. The search continues because the reward, Understanding the conditions that make planets breathe transcends any single discovery. Whether this rocky neighbor carries a transient veil of steam or simply reflects moisture from its star, it has already demonstrated how delicate the balance is between heat and gravity, between survival and loss. Each measurement refines this balance, inching science toward the point where numbers become knowledge. And like a like, it helps the channel grow and makes a huge difference.